In this session, we will derive the dynamics of mechanical system. So most of the mechanical system are constructed by mechanical components. So mechanical components such as damper, spring, right? So the mechanical systems are constructed by the mechanical components such as damper and spring. The dynamical equation, as we have seen earlier, can be derived either by Newton-Euler or Lagrangian-Euler method. But the dynamical equation of the system, when it is derived by using Newton's law of motion, Newton's law of motion becomes more complicated especially when you have more number of masses. If the number of masses of the mechanical system is more, then this approach will become complicated. So we'll be using a Lagrangian Euler method for deriving the dynamics of the mechanical system. The Lagrangian equation for deriving the dynamics of the mechanical system is given by Qi is equal to d by dt of dou L by dou Qi dot minus dou L by dou Qi, where I will be equal to 1, 2, etc. up to n, where n refers to the number of masses. So Qi is the generalized coordinate, and capital Qi, it is the generalized force. And L, as you know, it is the Lagrangian. So this is the dynamic equation for deriving the dynamics of a mechanical system using Lagrangian Euler method. Now let us consider a dynamical system and derive the dynamics. So we will consider a mechanical system with K representing the stiffness of the spring and B representing the damping coefficient of the damper, and let m be the mass of the moving object, and let f of t be the force exerted on the object, and the resultant displacement, let us represent it as x. Right. So we are deriving the dynamics by using Lagrangian method. So for that we need to determine the kinetic energy and potential energy. So as you know, Lagrangian is not ideal for non-conservative forces. That is, the forces exerted due to the frictional component. You cannot model it. So we will be just considering the force exerted by the spring. So we need to calculate the elastic potential energy. The elastic potential energy. So the elastic potential energy is simply the work done to stretch or compress the spring, and it depends upon the spring constant K. So and also the distance that it is stretched, right? So elastic potential energy, it is the work done to stretch or compress a spring, and it depends upon the spring constant K and the distance to which it is stretched. So the force required to stretch the spring, it is proportional to the amount of stretch. It is proportional to the amount of stretch. So we can write this as force is equal to K into X. K is the spring constant. So the force, it will vary or linearly or increase linearly from 0 at the start to Kx in the fully stretched position. So this is for fully stretched position. Now if you just determine the average force, so the average force will be Kx by 2. The average force will be Kx by 2. So that's the elastic potential energy, we can represent it as we have got the force. So kx by 2, that is the force into the distance to which it is stretched. So it will be kx squared by 2, right? Kx squared by 2. Now coming to the kinetic energy. So the kinetic energy is equal to, it is simply half into m, that is the mass of the moving object, into velocity. So velocity, as the position is x, so the velocity will be x dot square, right? So now we will get the Lagrangian. So Lagrangian, as you know, K is equal, sorry, L is equal to kinetic energy minus potential energy. So that is equal to half into mx dot squared minus kx squared by 2. So we also have to determine the, uh, to derive the torque equation, we also require dou L by dou x dot and dou L by dou x. So dou L by dou x dot. So as you see in this Lagrangian, you have two terms. So in which you have one, in the first term has x dot term. So the second term on differentiating will become 0 with respect to x dot. So here we will be getting dou L by dou x dot will be equal to simply m times x dot, right? And dou L by dou x will be equal to minus k times x. So you will be getting the first term on differentiating with respect to L becomes 0. So you will be getting only we have to differentiate only the second term, which will be dou L by dou x is equal to minus k times x, right? So the dynamic equation becomes, so Q of T will be equal to, as we have said earlier, Q of T is equal to d by dt of dou L by dou x dot minus dou L by dou x. So which we get as d by dt of dou L by dou x dot. So which is simply mx double dot, right? So mx double dot minus dou L by dou x. So here my dou L by dou x is minus kx. So we'll be getting plus kx, right? So far we derived the force encountered by the spring element and the mass whenever an external force is exerted. So as the mass m encounters the external force, force is also connected by the damper. So the force connected by the damper will be equal to B into x dot of t, right? So as per Newton's law of motion, as per Newton's law of motion, the force that is exerted on the object will be equal to sum of all uh, forces, that is Q of T in the opposite direction. So Q of T plus the damping force, that is B into x dot of T, right? So already we have derived Q of T, which is m into x double dot of T plus k into x of T plus v into x dot of t. So this is the dynamic equation of the spring mass and damper system.